All right, so we have this unit and one more unit. Woo! And that's it. And then we'll start the whole review process. So the really good news about this unit, it's super quick and it's super easy because you've already done the majority of the learning in the first time we did thermochemistry, where we did enthalpy. So all the things you did in enthalpy, like using Big Mama, the flippy thing, all that kind of stuff is going to apply, but instead we're looking at entropy and Gibbs free energy, and we're putting it all together. Okay? So where is my little thing? I'm losing it. I'm losing my mind. All right, so this is a quick review. You need to know the first few laws of thermodynamics. The first law of thermodynamics says energy can't be created or destroyed, and you can see that is represented by this. This is basically saying that the energy of the system, meaning the reaction, is equal to the opposite of the energy of the surroundings. And we already know that. Energy leaves the system, it goes to the surroundings. If it leaves the surroundings, it goes into the system. So they're equal and opposite. You already know what enthalpy is, aka heat of a reaction, delta H. Delta H of the reaction can be calculated. What did we call this? Big Mama. This can also be applied. We can use Big Mama to find both delta S and then delta G at 25 degrees Celsius. We're going to learn about why delta G is special later, but that little knot up there stands for standard conditions. What's the standard conditions in thermo? Yep, 25 degrees Celsius or 298 K and 1 atmosphere. Good. The little f stands for heat of formation. Good. Who remembers what heat of formation is? Forming what? 1 mole from its, you wrote heat of formation reactions where you made 1 mole of the substance from everything on the left was 0, enthalpy of 0. So what were you forming it from? Not nothing. It's elements. Okay. So when you form 1 mole of a substance from its elements, that's called the heat of formation. So on your thermo tables, that column is basically that it goes with the reaction of forming 1 mole from the elements. We know exo and endothermic. You need to know that delta H is negative if it's exo, delta H is positive endo. Again, all review. Here we're talking about exo and endothermic. Heat is entering if it's endo, heat is exiting if it's exo. Right? So that stuff you already know. What we're going to look at today would be something called entropy. And this is the second law of thermodynamics that states the universe, for any spontaneous process, the entropy of the universe is positive. Meaning the universe tends toward disorder. And that's what entropy is. Disorder. If you don't believe it, how long does it take a clean room to get messed up? Yeah, about 5 minutes. So nature tends toward disorder, and for a reaction to be spontaneous, we have to have a delta S of the universe that is positive. On the sideboard here, and I know those at home can't see it, there's going to be ways we can tell if something is spontaneous, a system or a reaction, and one of them is utilizing the delta S of the universe. If the delta S of the universe is positive, it's spontaneous. We're going to get to delta G soon, and if delta G of the system, not the universe, the system is negative, it's spontaneous. And then next unit we're going to talk about E, which is volts, and what kind of battery works? A battery with a positive voltage. So a positive E is spontaneous. And then if we're spontaneous in the forward direction of an equilibrium system, K is greater than 1. So all these things talk about spontaneity. I get concerned because this universe thing, people forget about. They think that they can just use the delta S of the system, which using Big Mama, to find the delta S of the system to determine if something's spontaneous. No. You can have a delta S that's negative and it still be a spontaneous reaction, a delta S of the system. So you have to look at the delta S of the universe to determine spontaneity. Okay? And then how do we calculate that? We'll get to that in just a second. So the first way we're going to calculate delta S of the system, and this is of the system, is the use of, what is that again? Big Mama. Big Mama can be used at any temperature for H or S. Delta H and delta S, they are not temperature dependent. So we can use Big Mama all the time for these guys. We're going to have a limitation with delta G, and we'll talk about that on Monday. But we can use Big Mama at any temperature and find delta H or delta S of the system. So in order to calculate delta S of the universe, as on the other page, delta S of the universe is equal to delta S of the system plus delta S of the surroundings. Well, we know how to find delta S of the system using Big Mama. How do we find delta S of the surroundings? Well, here's this equation. Delta S of the surroundings is equal to delta H of the surroundings divided by T. That confused. Why is that? Well, one thing I want you to notice that's important about the delta S on the table, the units on delta S are joules per mole K. There's a temperature factor in there. The delta H on the tables is joules per, or kilojoules, excuse me, per mole. So we need to divide by temperature to make this a delta S. So my question to you is, how do I find delta S of the surroundings? Well, I need delta H of the surroundings. Have you ever done delta H of the surroundings before? No. What did you calculate delta H of last time we did this? The system. That's heat going into or out of the system. So if I know the delta H of the system, how does that relate to delta H of the surroundings? Exactly, it's opposite. So my real equation for delta S of the surroundings is this. I take the opposite of the system, which I know how to do, Big Mama, opposite, and divide it by the temperature. So that gives me delta S of the surroundings, add it to delta S of the universe, delta S of the system, and that gives me delta S of the universe. Okay? Well, we're going to do one of those, so you'll see it. The next is just repeating what I just did. All right? Okay, so now you need your calculator. Well, you probably don't need your calculator for this one. Actually, if you use your calculator for this one, I'm going to be concerned. Calculate the delta H of the reaction for the following chemical reactions. So we have all our numbers. What do we do? Big Mama, products minus reaction. So we get 1 times AlCl3 is negative 704 minus, oh Lord, 1 times 0 plus 3/2 times 0. What's our answer? Negative 704. I have to have units. Kilojoules per mole. All right, so this is an exothermic reaction. Yes, Grant? Yep, they're different. That's a very good point. This is kilojoules per mole. When we get to delta S, those units are going to be joules per mole K. So whenever we put this in the equation with a delta H, either in the universe equation or in the Getto-Homey equation, which we're going to talk about on Monday, we have to change one of them to be like the other. And that's the biggest student mistake. As I've graded the AP, students don't pay attention, just shove them together. They're not even the same unit. You have to watch the units, okay? All right. Now we're going to predict whether the entropy of the system increases, remains constant, or decreases when the following processes occurs. All right. Explain your reasoning. Ice melts at 0 degrees Celsius. Predict the entropy. What is another word for entropy? Disorder. So I want you to ask yourself, does disorder increase or decrease? Think molecularly what's going on. Increase. So ice melts, so this is an increase in disorder. Now, as far as the sign of delta S on that process, our delta S of ice melting is going to have a positive value. If disorder is increasing, that's positive. That's how nature goes. All right? So what? So no. Why is it not spontaneous? I'm glad you said that. This is just the system, okay? We don't know the delta S of the surroundings yet. You need to know both to figure out spontaneity. Okay? All right. A precipitate forms in an aqueous solution. We're going from liquid to solid, decrease. So the sign on our delta S would be negative. A solid dissolves in water, solid to ions. It gets crazy. Those ions start moving around. Disorder definitely increases. And then a gas condenses to a liquid. Disorder decreases. Delta S is negative. Okay, are we good with that? Now, another way you're going to be able to predict disorder is just by looking at the equation. So before we actually calculate this, I want to look at the states of matter, and let's predict the sign on that delta S. We're going from aluminum solid and liquid to all aluminum chloride solids. It's a decrease in disorder. So we should hopefully calculate a delta S that is negative. So now we're going to actually calculate it using the numbers on the previous thing. And one thing I need you to watch out for is your delta S of free elements. They're not zero like they are in delta H world. So we need to make sure we get those. So we have 1 times, what was aluminum chloride? 111 joules per mole K. So that's products minus 1 times 28 plus 3/2 times 223. Thank you. So what is our delta S? They got last class negative 351. Check it. It's first period. Welcome back to the world. You look good in that color. What? Negative 351. Good. All right, are we good with that? All right. Now, consider the following reaction. The reaction is carried out at 100 degrees Celsius. That could be meaningful, maybe, maybe not. It depends on what they're asking for. Calculate the change in entropy. So we're looking for our delta S, change in entropy, of the system. So that's a big mama question. Delta S is not temperature dependent. I don't care if it's at 100. I can use big mama. Now, let's predict the sign, though, before I actually do this. Let's predict the sign of our system. We're going, well, I'm just not going to say anything. What do y'all think? It's gases to gases. No, it's not nothing. Why is it decreasing? Less moles of gas at the end. So we're starting out with 4 moles. Think of 4 of you running around in here, and then 2 of you leave, and we're left with 2 of you running around in here. There's going to be less disorder with the less moles of gas. So we're hoping that the delta S is, oops, wrong. Delta S is negative. All right, so let's go ahead and set it up. I went ahead. You guys have a thermotable in the back of your in-class problems. Just know that. That's a very small thermotable. Any problems that you get to in the homework that you need extra values for, there's an extended table in the back of your book. There's also something called the internet. If you type in entropy of, it'll pull it up right away. Siri does it. I've done that before because I'm that kind of nerd. What's the entropy of blah, blah, blah? Let me work on that, and then it comes up. So, or Wolfram Alpha, any of those, okay? So I'm not giving you license to go, oh, I don't have delta H, I'm not going to do the problem. Look it up, all right? The back of the book is honestly the best thing. Just get your book out when you're doing your homework, and it'll be right in front of you. And it's got an extensive table in the back, in the appendix. All right, so if we're going to do products minus reactants, I went ahead and wrote it on the board. So delta S is equal to 2 times ammonia is 193 joules per mole K minus 1 times 192 plus 3 times 131. So go ahead and calculate that. They got negative 199. I want you to check it, though. Joules per mole K. Yeah, awesome. Okay. Can we tell if it's spontaneous yet? What do we need to know for spontaneity? Delta S of the universe. This is only of the system. Now it says, okay, go ahead and calculate the change in entropy of the surroundings. All right, what was the entropy of the surroundings again? Negative delta H of the system divided by T. I'll tell you a way to remember it, because this is not on the AP equation sheet, unfortunately, and you need to remember it. Think about the unit difference between the two numbers on the table. What is delta H missing to be like delta S? That temperature. So just think about having to divide by temperature. And as far as the delta H goes, just remember, since it's the surroundings, it has to be opposite to the system, and you know how to do the system. So that's why we have a negative delta H of the system. So first thing I'm going to do is find the delta H of the system and plug it in on top. What is the temperature, though? 373 Kelvin. Because it's 100 degrees Celsius, we have to be in Kelvin. So I'm going to go ahead and do the delta H of the system over here out of the way and then plug it in there. All right, so it is 2 times, this is not hard because we got a lot of zeros, plus blah, 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 0. So we get what? It's 46.2. Negative 92.4. And the units on this are what again? Kilojoules per mole. All right. So this is of the system. But if I'm going to plug it into the surroundings, I need to make it. No, not yet. We'll get to that. I got to make the opposite of that, right? So this is going to be positive 92.4 divided by 373. So what is the official entropy of the surroundings? 248? They got 228 last time. 248. See, I told you. 248. What are the units on this? Kilojoules per mole K, because we divided by that temperature. Not right now. Not at this point, because at this point, all we're doing is changing it. All we're doing is calculating entropy of the surroundings. We will next, because now it says the universe. And so to calculate the entropy of the universe, we take delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So now we would have to make sure that they're going to be the same unit. So delta S of the universe is equal to, what was my delta S of the system? Negative 199 joules per mole K. This is where they have to be the same. A lot of people say, which way should we go, joules to kilojoules or kilojoules to joules? It's just in your best interest the majority of the time to go to joules, because later we're going to deal with the, remember the energy R? 8.314 joules per mole K. A lot of times that's what we're going towards, so just go to joules. Make it your personal rule to go to joules. So that then we're going to add to, this was our delta S of our surroundings. So what do I want to do? Right, 248 joules per. So now the units are the same. Now we can add them up. So my delta S of the universe is equal to 49? Oh, that's right, because they got a different answer last time, but that was because this other thing was messed up. So 49 in my units per mole. Now the question, part D, this is part C, is the reaction spontaneous? Why? If you just tell me delta S is positive, I'm going to lose it on you. Yes, because delta S of the universe is positive. You will see a problem like this. And they're not hard. You just need to pay attention to the universe thing to determine spontaneity. All right? Are we good in the hood? Questions? Okay, you have a quick little homework. On your homework, one thing that they brought up last period, there's this weird thing. It says S, sulfur, rhombic. It says rhombic, and then it says solid. They're like, what is that? Rhombic. It's just a sulfur solid that's crystalline shape is rhombic. It's just solid. Okay? Know that that's just weird. All right, we are done.